I know. The hair, yeah, yeah. I told him to take off this much. He ended up leaving this much instead. Anyways. Oh, oh yeah, gravitational potential and shit. So this is basically a conclusion I reached while studying like gravitational potential. It's not very, it's not based on a lot of math. It's just based on like knowledge. So please, in the exam, do not try this. Please do not blame me for the wrong. Okay, that's the disclaimer. Glad I put this out of the way. Let's get moving. So, first of all, what's gravitational potential? So, to understand gravitational potential, we have to understand what a gravitational field is in the first place. So, a gravitational field is an area or a space around an object where you will experience or you will see that a force is being exerted. So, in the case of gravity, you got the Earth, it's pulling us downwards, and yeah, nothing new here. So, what is gravitational potential exactly? So, usually when you look it up, it's the work done per unit mass to bring a mass from infinity to that point. Doesn't make any sense. So, I think the best way to explain this is first by understanding like the strength of the field as the distance from the object varies. So let's say you got an object, okay, it's in the center. So the further away you get from the object, the weaker the field gets. Like imagine you got a magnet, okay, and you got an iron nail. So the further away you get the iron nail, the weaker the attraction to the magnet is going to be. So this is the same for the gravitational field. The further you go away, weaker it gets until like when you reach a really, really fucking far distance, you wouldn't have a gravitational field anymore. And this like extremely far distance, we can just imagine it being and like an infinite distance away from that object. So if you go like so fucking far away, you're not going to have like any forces from the gravitational field. So I guess a better way to even explain the gravitational potential is that it is sort of like it is a property of the field that determines the work done on the object depending on its position. And this is basically like the definition of the word potential, which is other than it being something you're failing to achieve, it is something that's dependent on position. Like that's what potential is. It's something that's position dependent. So, oh yeah. So why is it negative? So we said that when you're like an infinite distance away from your object, you're not gonna have like any field. It's not gonna be in the field. It's gonna be out of the field. So it's not gonna experience like any sort of like force or something. Um, so at this point, the gravitational potential is going to be zero because like there is no work to be done. There's no force. There's no attraction. There's no nothing. So the potential is going to be zero. So that means inside the field, okay, so outside the field it's zero. Inside the field, it's got to be less than zero. Because when you go away, it comes closer to zero. Move backwards, it's going to be less than zero. That means it's negative. That's the traditional way of thinking of it, which is perfect. Now I found a retarded way, and it's not based on any math or anything or any of the mechanical engineering integration kung fu that you guys do. It's very like humble, and it comes down to direction, like vectors and shit, like you know Let me draw it. And go. Let me just clean up the board a bit and draw this out. So if you got an object, hang on, thing is it keeps falling off like the tip of the pen. Okay, there we go. So you got an object. Let's draw this point. Okay, you got this sort of scale, this distance scale. Okay, it's going to be like that. And let's say here is 5 units. Here is zero. Okay, so just put it in a picture. Hope this is visible. I don't know. I can't really see it. Anyways, so if let's say you got a dot. Okay, I don't know if you can see this little dot next to the object. Okay, so if you want to push that dot, what you can do is you can move it from point zero, a point where the displacement is zero, to a point where the displacement is five. So the initial position is going to be zero. Final position is going to be five. So what's the displacement? It's the final position minus the initial position. So it's going to be the five minus the zero. But in the case of gravity, what's going on is like the object is not pushing the other object away. Like the Earth is not pushing us away. It's actually attracting us. So if you got an object in space and the Earth were to attract it, what's going to happen is the initial position of the object is not on Earth. It's away. It's like five. It's going to be here at the five, and it's gonna end up, let's say, crashing on Earth. So the final position is going to be the zero. What does that mean? That means that the displacement is negative, which makes a lot of sense now. Or maybe it doesn't, and I'm just crazy. So I guess my idea is built on the fact, or the assumption, rather, that the energy is going to be, or the work done is the force times the distance, and we know that the gravitational force is equal to minus the gravitational constant times the mass times the other mass over the separation between them squared. And the separation here, I'm assuming it's the displacement. So if the displacement is going to be squared, then the sign doesn't matter. But technically, we're talking about a force, and the force is a vector, so the direction does matter, but the displacement doesn't. So I guess it's a way to compensate. Like the negative sign could be a way to compensate for the lack of direction in the displacement. And I know there's like all this mechanical engineering kung fu that you can do and like integrate and blah, 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 limits and all. But this is like just an oversimplification, I guess, or just an observation. Yeah, yeah. We don't even know if gravity is real because maybe it's just the object warping like space time and like general relativity. Einstein. World's confusing.